Hello guys, welcome to today's video. In this video, we will be looking at the different modulation schemes that are used in 5G and 4G. By the end of this video, you will understand why exactly 5G uses the modulation schemes that it does. Why does different channels use different schemes? What is pi by 2 BPSK and why was it introduced? Let us get into it. Let us start with the most fundamental concepts. How are modulation symbols mapped onto resource elements? How are these resource elements mapped to waveform before they are generated and transmitted across air interface? A resource element is the fundamental unit of a 5G resource grid. In 4G, one resource element is defined as one subcarrier in frequency domain and one symbol in time domain. You can think of it as a single cell in a grid. Each resource element carries exactly one modulation symbol. This symbol itself is a complex number. It has a magnitude as well as a phase. And its position in this constellation diagram determines which bit it represents. If you haven't heard about constellation diagrams before, I'll explore that in the coming slides. How are the number of bits per modulation symbols determined? This is calculated based on this formula, that is log m to the base of 2. 5GNR fundamentally uses two different modulation schemes. There is PSK or phase shift keying and QAM or quadrature amplitude modulation. QPSK carries exactly 2 bits per modulation symbol. In 16 QAM, one symbol carries exactly 4 bits. In 64 QAM, one symbol or one resource element carries exactly 6 bits, and so on and so forth. Here is what makes this powerful. Adjacent resource element on the same slot can carry symbols from completely different modulation schemes. This is because different physical channels, there is PDSCH, there is PUSCH and PUCCH, occupy different arrays, and each channel has its own modulation rules. The spec defines the rules per channel, and that's exactly what we will cover next. This table is the core of 3GBP 38211.2.7 section. It maps every modulation scheme to every physical channel. The first thing to notice is that QPSK is the only scheme that appears across all the physical channels. All PUSCH, PUCCH and PDSCH uses QPSK. QPSK is the baseline. Every channel must be able to use it. Now look at the higher order schemes, 16 QAM, 64 QAM and 256 QAM. They only appear on the data channels PUSCH and PDSCH. They never appear on control channels. But why? This is because data channels are scheduled to the UE only when the network knows the UE has a good enough signal for reception. Control channels must be received by every UE in the cell, including those at the cell edge. Now let us look at an unusual entry, that is pi by 2 BPSK. It only appears on PUSCH and only under a specific condition. This is that DFTs or FTM must be selected for transmission on PUSCH in order to use pi by 2 BPSK. And then there is BPSK. Only PUCCH format 1 uses BPSK. This is the format that is used to carry a single bit of information, an ACK or an ACK. 1 bit means only 2 possible states. BPSK is a natural choice with 2 constellation points. Every entry in this table reflects a trade-off between spectral efficiency and reliability. Thus, we have our data channels PUSCH and PDSCH. They carry your data, your video, your files and everything. And they support the full range of modulation orders specifically because they are scheduled resources. The network only assigns them to the UE when it is in connected state and when it knows that the UE has a good enough channel quality. So in 6G, the proposed modulation orders for PDSCH is up to 1024 QAM. So that's the downlink data channel. For PUSCH, the modulation order will be much lower. 5G supports up to around 256 QAM in release 18. On the PDSCH, the base station selects the modulation scheme every scheduling interval, every slot based on the channel quality indicator that the UE has reported. If you are standing next to the base station with a good enough channel quality, then you will get 256 QAM. That means you will get more bits per resource element per symbol, and thus you will have a significantly higher throughput. But if you walk towards the cell edge, then the scheduler steps you down based on the CQI that is reported by the UE. You'll probably come down to 64 QAM or 16 QAM. This means the throughput will be lower. Thus, the base station is always keeping you at the highest modulation order with the signal quality that you can support. On PUSCH, the same logic applies. But there is one entry that is not present in downlink. There is pi by 2 BPSK. So pi by 2 BPSK, as mentioned previously, is used only with DFTS or FDM with one layer. And the fundamental reason behind this is the power constraint problem of the UE. The UE is a power constraint device. So your phone has a small amplifier that is running on a battery. So the base station has a huge amplifier with active cooling and then grid power, but then the UE doesn't. Therefore, power efficiency is of utmost importance to the UE. So pi by 2 BPSK is a scheme that reduces the PAPR along with DFTS or FDM. PAPR stands for peak to average power ratio. We have discussed this thoroughly in our waveform video. I'll provide a link to that video in this channel, in this video. Now let us look at the control channels PUSCH and PRACH. These are fundamentally different from the data channels, and the modulation choice reflect that. PUSCH has different formats based on the bits that it carries. PUSCH format 0 has no modulation scheme at all. Instead of mapping bits to constellation points, the UE selects a specific sequence from a set of pre-allocated sequences. If you have 4 sequences to choose from, selecting one of them communicates 2 bits of information. The choice itself is in the message. So this means that format 0 can be decoded at a very low SNR because the receiver only needs to identify which sequence was transmitted. It does not need to decode a constellation point. Format 1 uses BPSK. So this means that 2 bits can be mapped to one resource element or one symbol. It can carry a single bit, ACK or NAC. If there are 2 bits, it switches to QPSK. This scheme is determined by the payload size. So BPSK corresponds to 2 constellation points. Now format 2 always uses QPSK. It carries larger payloads. It carries the channel state information, the CSI, multiple HARC acknowledgements. So it produces a series of QPSK symbols across the allocated resources. Then format 3 and 4 always gives the G0B a choice. It can configure the UE to use pi by 2 BPSK or QPSK. If the UE is at cell edge, then it will use pi by 2 BPSK, and since coverage is the highest priority there. Otherwise, it uses QPSK. And finally, we have PRACH. PRACH corresponds to the random access channel. It has no modulation scheme whatsoever. It transmits a set of choose sequence. So the information is not in amplitude or phase domain as is with the constellation diagrams or as is with any of the modulation schemes. So the information is in which sequence is selected, and this sequence is also used for uplink timing alignment. This slide actually answers almost all the common questions that you might have had till now. What exactly is the constellation diagram? How exactly does it look? And why exactly does pi by 2 BPSK exist? So the answer as to why pi by 2 BPSK exists is in the power amplifier. So standard BPSK has two constellation points. There is this point 0 and then we have point 1. And this corresponds to +1 and -1, corresponding to the bits 0 and 1. When the transmitted beam switches from 0 to 1 or from 1 to 0, it has to go through this zero crossing. So at zero crossing or zero amplitude, there is a sudden change in the signal envelope. But power amplifiers are designed to operate in the linear region. When the signal envelope has large peaks or high PAPR, PAPR stands for peak to average power ratio, the amplifier must back off its average output power to prevent the peaks from hitting the non-linear region. If it hits the non-linear region, then this might cause distortion. So operating backed off means there is wasted power. There is more heat, and on a UE there will be shorter battery life. So pi by 2 BPSK solves this by rotating the constellation 90 degrees for every consecutive symbol. So if the symbol n uses a real axis, then the symbol n+1 uses this imaginary axis, and so on and so forth. The maximum phase shift between two consecutive symbols is 90 degrees. So here in BPSK it is 180 degrees. The signal amplifier, the signal envelope never passes through the 0. So the PAPR reduces significantly. Pi by 2 BPSK actually transmits the same number of bits per symbol as BPSK. It transmits only 1 bit. But this is a much more friendly waveform for the UE power amplifier. This is why the spec restricts pi by 2 BPSK for DFTS or FTM. So this combination of both techniques gives maximum PAPR reduction for the uplink. Now let us look at gray coding. Gray coding is one of those concepts that might sound simple, but it has a profound effect on system performance. The rule is that in the constellation diagram, any two adjacent points, that is points that are nearest neighbors, they must have bit labels that differ exactly by 1 bit. So look at this 16 QAM constellation. So here each symbol or each resource element can transmit up to 4 bits of information. Take the point labeled as 1000 and its horizontal neighbor 1001. They differ only in the last bit. Now take 1000 and take its vertical neighbor 1010. So they also differ in exactly 1 bit. Here the second bit is different between these two. Now ask yourself, what would happen if a receiver makes a mistake? In any system, in any radio system that is operating near its SNR threshold, the most likely error is confusing a symbol with its nearest neighbor, which is the closest point in the constellation. So gray coding guarantees that this probable error cost exactly 1 bit and not all 4. This matters enormously when you consider the channel decoder sitting behind the demodulator. So 5G NR uses LDPC codes for data channels. So LDPC is very effective at correcting a small number of error bits per code word. So gray coding gives the best possible output. So it guarantees that the error bits would not be more than 1, or that the errors would be as localized as possible. So without gray coding, a single symbol error, a single bit error could flip all the 4 bits in a 256 QAM or a 16 QAM symbol simultaneously. The LDPC decoder sees 8 errors in one shot. This is much harder to correct. So gray coding turns that into a 1-bit error, which the decoder will be able to handle easily. Now let us look at the physical channels. Which modulation scheme does the physical channels use when compared to the physical signals use when compared to the physical channel? The answer is that physical signals does not use any modulation schemes. This is an important distinction. We have the physical signals. We have TMRS, PTRS, CSIRS and SRS, and none of these use any modulation schemes at all. They are mapped directly to the allocated resource element without going to the modulation mapper. Think about what this happens, what would this mean in practice. If you look at a resource grid, not every resource element carries a modulation symbol from a channel like PDSCH or PDCCH. Some resource element might carry signal sequences. So these sequences are known and they can be calculated. So at both the transmitter and the receiver, that's what makes them useful. Take DMRS for example. DMRS is used for demodulating data channels and the PUSCHs. The receiver knows exactly what complex numbers the transmitter sent on the specific resource element for DMRS. So comparing what it expects, what it receives versus what it expects, what it is to be expected, it can estimate the channel and how the propagation environment distorted the signal. The channel estimate is then applied to the data resource elements to demodulate the actual symbols. Then we also have a sounding reference signal. So this is the mechanism by which the G0 B, the base station, learns about the uplink channel across the full bandwidth. So this is critical for frequency selective scheduling and massive MIMO beamforming decisions. So none of this goes through any modulation scheme. So they are just infrastructure, just scaffolding to make data modulation and demodulation as reliable as possible. Now let us bring it all together. There are 6 points that you must fundamentally remember when you leave this video. The first one is that modulation symbols are mapped to resource element. One resource element consists of exactly one symbol. The symbol is a complex number. The symbol is a point on the constellation diagram. Number 2 is that the modulation scheme determines the number of bits that are mapped per symbol. This is log m to the base of 2. We have QPSK till 256 QAM, which determines how many bits are mapped onto one symbol. Number 3. PDSCH and PUSCH, the data channels, get the full range of modulation schemes. They get QPSK till 256 QAM till 1024 QAM in 6G if possible. They are the scheduled channels. They are assigned to UEs whose channel quality is already known. So link adaptation, by making use of CQI or other parameters that are reported by the UE, picks the best possible scheme at every slot. Number 4. PDCCH and PBCH uses only QPSK. Controlled information must be decodable by the UE in every cell, including even those at the edge. The lower the modulation order, the lower the coding rate and maximum coverage. Number 5. Pi by 2 BPSK exists to solve a real hardware problem at the UE. Pi by 2 BPSK is used for optimizing the UE power amplifier when DFTS OFDM is used for reducing PAPR or peak to average power ratio. By rotating the constellation 90 degrees, every symbol, zero crossings are eliminated and PAPR drops. Number 6. Gray coding protects all modulation schemes. Adjacent constellation points differ in exactly 1 bit. So the most likely error is that the decoder misidentifies a symbol to its nearest neighbor, and if it does that, then this, by using gray coding, it means that this would cost only 1 bit. So LDPC and polar decoders handle 1 bit errors very well. That was a brief overview of the modulation schemes and why they are used as they are in 5G systems. So if you have followed this, you have probably understood the modulation schemes of 5G NR from the spec level, along with how the encoder or decoder plots them onto the constellation diagram. Thank you for watching, and see you with a new video next week.